Hello friends, welcome to True Event Academy. In the last lecture, we have completed the discussion on the work energy principle. So in this particular lecture, we will start discussing principle of conservation of linear momentum. So first we will discuss the concept of momentum. After that, we will discuss the principle of conservation of linear momentum. Okay, so let us discuss momentum. So how we can find the momentum of a particle. So let us consider a particle of mass m and its velocity at any instant is t. So the vector mv is known as the momentum vector, and the direction of this momentum vector is same as that of velocity vector, same as that of velocity vector. Okay, so the direction of momentum vector is same as that of the velocity vector. And how we can find the momentum? So just take the product m into v vector is known as the momentum vector, and its direction is same as the velocity vector, as simple as that. Okay, so let us discuss the principle of conservation of um, linear momentum. Okay, so what is the statement? If the sum of resolved parts of the forces acting on a particle in motion in any given direction is zero, then the resolved parts of the momentum of the particle in that direction remains constant. So how we can prove this? Let us prove this statement. So let us consider a particle of mass m, and let us consider a force F is acting on this particle. Okay, so it is given that the resolved part of this force along a direction. So let us consider a direction a vector. Okay, so the resolved part of the force along a vector is F dot a. Okay, so the resolved part of this force F that is acting on this particle along this a vector is zero. This is given as zero. This is given in the statement. Okay, what we have to prove? To prove is that the momentum along a vector is constant. This we have to prove. So let us differentiate this. The momentum along a vector is how we can find the momentum. Suppose the velocity of a particle is v vector and its mass is m. So mv vector is the momentum vector. So we have the momentum vector as mv vector, and its resolved part along the direction a vector is dot a cap. Okay, so let us differentiate this. D upon dt of mv vector. This is equal to m d upon dt of v vector dot a vector. So we have this as m into, let us apply by parts. So dv upon dt dot a, okay, plus v vector dot dA upon dt. And we have a is equal to constant vector. So dA upon dt is equal to 0. Our a vector is constant vector. So the differentiation is 0. So this will get vanished. So we have this as m dv upon dt dot a. And from Newton's second law, this is our force. So we have F dot a vector, F dot a vector. So we have d upon dt of mv vector dot a. Okay, so this is the resolved part of the momentum along direction a is equal to F dot a vector, and this is given as 0. So this is equal to 0. Hence we can say that d upon dt of resolved part of resolved part of momentum along a vector is equal to 0. समझ में आ रहा? This means resolved part of momentum along a cap is equal to constant. Okay, so differentiation of something is 0. This means this particular term will be constant. Okay, so this is the proof of this principle of conservation of linear momentum. Okay, let us discuss some questions on this topic. What is given in question number 1? A shot of mass m is fired horizontally from a gun of mass capital M with velocity u relative to the gun. Okay, show that the actual velocities of the shot and gun are given by capital mu upon m plus small m and small mu upon capital M plus small m respectively, and their kinetic energies are inversely proportional to their masses. Okay, so to show, what we have to show? First, we have to show that the actual velocities of the shot. So let us consider the actual velocity of shot as a small v. This we have to show it as capital mu upon m plus small m and capital V. So let us consider the actual velocity of the gun with which it recoils. Okay, so this is equal to small mu upon capital M plus small m. Okay, and secondly, we have to show that the kinetic energy of shot upon kinetic energy of gun is equal to, it is inversely proportional. So it will be capital M upon small m. So these two expressions we have to show. So let us solve this. So what is given in the question? There is a gun of mass capital M and there is a shot of mass small m. Okay. So we have, let us consider the actual velocity of the shot as a small v and the velocity with which the gun recoils is capital V. Okay. So it is given that velocity of shot relative to gun is equal to small u, and small u will be equal to, so the relative velocity will be small v minus of minus capital V. This will be equal to small v plus capital V. This is question 1. Secondly, since there are no external forces acting in the horizontal direction, okay, so momentum will be conserved. So momentum will be conserved. So momentum before firing is equal to momentum after firing. Okay, so we have momentum before firing because this whole system is at rest, so this will be 0, and momentum after firing, so this is equal to momentum of shot plus momentum of gun. Okay, so this will be equal to m of small v uh, plus this is equal to, this is in opposite direction, so capital M into capital V. Okay, this is minus of mv. So we have small mv is equal to capital mv. Okay, this is equation 2. So let us solve these two equations for getting the value of small v and capital V. So we have the equations as u is equal to small v plus capital V, and secondly we have m small v is equal to capital M into V. So let us solve these two equations. Okay, so we have small u is equal to capital V, sorry, small v plus capital V, and from here we have small v is equal to m capital V upon small m. So let us place this. U is equal to capital M V upon small m plus capital V. This is equal to m upon small m plus 1 into V. So we have capital V is equal to mu upon m plus capital M. Similarly, we have small v is equal to mv upon small m. So small v is equal to m upon small m into v. So v is mu upon m plus capital M. This gets cancelled. So we have small v is equal to capital mu upon capital M into small u upon m plus capital M. These are the values of the actual velocity of the shell and actual velocity with which the gun recoils. Okay, so let us show the second part, that is kinetic energy is inversely proportional to their masses. Okay, so we have um, a small v, that is velocity of shell, is equal to capital M u upon m plus capital M, and capital V is equal to small mu upon m plus capital M. Okay, so let us take the ratios of their kinetic energy. So we have kinetic energy of shot upon kinetic energy of gun is equal to half into small m into shot का velocity क्या है, small v square upon half of capital M into capital V square. This is equal to m upon capital M into V square upon capital V square. This is equal to m upon capital M into value of u is this one. This is equal to m square u square, and m plus capital M will gets cancelled. Okay, so no need to write this. So we have m square into u square. The u square gets cancelled. This gets cancelled. Capital M gets cancelled. This is capital M upon small m. So we have kinetic energy of shot upon kinetic energy of gun is equal to capital M upon small m. So kinetic energy of shot is inversely proportional. So from this expression we have kinetic energy of shot is inversely proportional to 1 upon small m, or kinetic energy of gun is inversely proportional to 1 upon capital M. Okay. Okay, so let us discuss question number 2. A gun is mounted on a gun carriage movable on a smooth horizontal plane. Okay, so there is a gun carriage and there is a gun that is mounted on this. Okay, and the gun is elevated at an angle of alpha to the horizontal. Okay, a shot is fired and leaves the gun in a direction inclined at theta to the horizontal. So let us consider a shot here. It is fired and leaves the gun in a direction of theta to the horizontal. Okay, so let us consider, so let a small m be the mass of shot, and capital M be the mass of gun plus carriage. Okay, so this is about the direction of, okay, this is the direction of actual velocity, okay, which is inclined at an angle of theta to the horizontal. So let small v be the velocity with the actual velocity of shot, and capital V be the velocity with which gun recoils. Okay, so this is capital V with which the gun recoils, and the mass of gun and carriage is capital M. And this is the actual velocity of the shot, and this is our shot. Okay, this is of mass small m. Okay, so let us now consider the relative velocity. Now let small u be the relative velocity. Okay, relative velocity, that is velocity relative to the gun. Okay, so u is the velocity relative to the gun, so its direction will be at an angle of alpha to the horizontal. This is u, and this is relative velocity, and this is actual velocity. So this direction is at an angle of alpha to the horizontal, and this is same as the inclination of gun with the horizontal. Okay, so um, now we have the shot actual velocity of shot in horizontal direction is equal to actual velocity of shot in horizontal. This is v cos theta. Okay, so now relative velocity of shot in horizontal direction will be small v cos theta minus capital V. This is equal to v cos theta plus capital V. Now we have relative velocity of shot in vertical direction. This will be equal to small v sin theta. Okay, so now we have u as the relative velocity. So the angle of inclination of relative velocity with respect to the horizontal will be, so now angle of inclination of shot with horizontal will be equal to small v sin theta. This is because this is relative velocity. This is relative. V sin theta upon small v cos theta plus capital V. Okay, and this is equal to tan alpha. Okay, because alpha is the inclination of relative velocity. Relative velocity is u. Okay, alpha is the angle relative velocity. Alpha is the inclination of relative velocity with horizontal. So tan alpha is equal to a small v sin theta upon a small v cos theta plus v. Let us further simplify this. So we have a small v sin theta upon a small v cos theta plus capital V is equal to tan alpha. So we have, let us divide by cos theta. So we have v tan theta upon a small v plus v upon cos theta is equal to tan alpha. Now let us apply the principle of conservation of linear momentum. Applying principle of conservation of linear momentum. Okay. So since there is no external force in the horizontal direction, so the momentum before firing will be equal to momentum after firing. So the momentum before firing is 0 because the whole system is at rest, and momentum after firing will be a small mv cos theta minus capital V. So this is equal to m small v cos theta is equal to, this is equal to capital M. This is equal to capital MV. So from here we have V upon cos theta. V upon cos theta is equal to M small v upon capital M cos theta. Let us place the value here. Okay, so we have, let us further simplify this. So we have small v tan theta upon small v plus v upon cos theta is M small v upon capital M is equal to tan alpha. Okay, so now we can cancel the small v. So we have tan theta upon this small v gets cancelled. So we have tan theta upon 1 plus small m by capital M is equal to tan alpha. So we have tan theta is equal to 1 plus small m by capital M into tan alpha. Okay, what is given in the question? If the mass of the gun and its carriage is b n times that of the shot. So the mass of gun and its carriage is capital M. So capital M is equal to n times of small m. So we have m upon capital M upon capital 1 upon n. So let us place m upon capital M as 1 upon n. So we have tan theta is equal to 1 plus 1 upon n into tan alpha. Okay, this is the same as this expression. Okay, so now let us discuss question number 3. So we have a shell of mass small m is fired from a gun of mass capital M, which can recoil freely on the horizontal base, and the elevation of the gun is alpha. So we have the gun like this. Okay, and this is of capital mass of the gun is capital M. Okay, and there is a shell of mass small m which is fired from the gun. So let the actual velocity with which shell of mass m is fired is small v, and actual velocity with which gun recoils is equal to capital V. This is capital V, and this is actual velocity is small v. Okay, and it is, let us consider the its angle of inclination as theta. Okay, now let small u be the velocity of shell relative to gun. So since we are taking the relative velocity, so the angle of inclination of the velocity, relative velocity will be alpha. This is the direction of relative velocity. So small u is the relative velocity. Relative velocity of shell with respect to the gun. Relative velocity of shell. This is actual velocity. Actual velocity. Okay. So we have so now the find the relative velocity along the horizontal direction and vertical direction. So velocity of shell relative to gun in horizontal direction. Horizontal direction is equal to velocity of shell relative to gun in horizontal direction. This is small v. Small v. This is small v cos theta minus of minus capital V, and velocity of shell relative to gun in vertical direction. Vertical direction. So there is no component of capital V in vertical direction. This is equal to, so this will be equal to small v sin theta. Okay. So the of inclination of u with horizontal is equal to tan alpha is equal to v sin theta upon small v cos theta plus capital V. So we have tan alpha is equal to small v sin theta upon small v cos theta plus capital V. Okay, so let us further simplify this. So we have tan alpha is equal to small v sin theta upon small v cos theta plus capital V. So this is equal to small v tan theta upon small v plus v upon cos theta. Okay. So let us apply. This is equation 2. Okay. So let us apply principle of conservation of linear momentum. Okay. Along the horizontal direction. Along horizontal. Okay. So there is no external force acting in the horizontal direction. So the momentum will be conserved. So the momentum before firing will be equal to momentum after firing. So momentum before firing is 0 and momentum after firing is m into small v cos theta minus of um, plus minus of m into capital V. So we have small mv cos theta is equal to capital MV. Okay, so we have um, capital V upon cos theta is equal to small mu upon m into small v, m small v upon capital V. Okay, so let us place here. So we have tan alpha is equal to small v tan theta upon small v plus v upon cos theta m small v upon capital V. This is small v. The small v gets cancelled. Sorry, this is capital M. No? Okay. So we have tan theta upon 1 plus m small m upon capital M. Okay. So we have tan theta is equal to tan alpha into 1 plus small m upon capital M. So we have tan theta is equal to 1 plus small m upon capital M into tan alpha. So here we have theta is equal to tan inverse of 1 plus small m upon capital M into tan alpha. Okay, this is the inclination of path of shell. Inclination of path of shell. Path of shell with horizontal. With horizontal. Okay. So now let us solve the part 2 of this question. Okay. prove that the let us write down first that equation of momentum. Equation of momentum. Equation of momentum. Okay, so we have momentum before firing is equal to momentum after firing. So we have 0 is equal to m into small v cos theta plus minus of m into capital V. So we have m small v cos theta is equal to mv. Okay. Now what is given in the question? Prove that the energy of the shell on leaving the gun is that of is 2, that of gun is m square plus. Okay. So we have the kinetic energy of shell upon kinetic energy of gun is equal to half of small m into small v square upon half capital M into capital V square. This is equal to m upon capital M into small v square upon capital V square. So from here we have uh, small v upon capital V is equal to small v upon capital V is equal to m upon small m into sec theta. So we have a small v upon capital V is equal to m upon small m into sec theta. No? This is sec theta. So we have a small v square upon capital V square is equal to m square upon capital M square upon small m square into sec square theta. So let us place here. So we have kinetic energy of shell upon kinetic energy of gun is equal to m upon capital M into m square upon small m square into sec square theta. So this is gets cancelled, this gets cancelled. This is capital M upon small m into sec square theta. Let us further simplify this. So we have the kinetic energy of shell upon kinetic energy of gun is equal to capital M upon small m into sec square theta. And sec square theta we can write as 1 plus tan square theta. And we have tan theta is equal to, so from here we have tan theta is equal to 1 plus small m upon capital M into tan alpha. Okay. This is 1 plus, okay, 1 plus small m upon capital M into tan alpha. So we have tan square theta is equal to 1 plus small m upon capital M whole square tan square alpha. So this will be equal to capital M upon small m into 1 plus tan square theta is 1 plus small m upon capital M whole square into tan square alpha. So let us further simplify this. Capital M upon small m into m square plus capital M plus small m whole square into tan square alpha upon capital M whole square. This gets cancelled. So we have m square plus small m plus capital M whole square tan square alpha upon m capital M. So we have kinetic energy of shell upon kinetic energy of gun is equal to this ratio. Okay, so this we have to prove. Okay, so we will discuss further questions in next particular lecture. Thank you.